Hi everyone, my name is Zhanwen. I'm a PhD student in Polytechnic Montreal in Canada. In today's talk, I'm going to present how to enhance structural anomaly detection by using a bounded autoregressive component in the framework of Bayesian Dynamic Linear Models. This work has been recently published in the Journal of Mechanical Systems and Signal Processing by Professor Goulet and me. We will firstly go through the context of this research, where we will see what are the anomalies in time series, what are the criteria of an effective anomaly detection method, and how it works. In time series, there exist two main categories of anomalies. The first one is called point-based anomaly, which refer to single data points that strongly deviate from a sequence within a time series. It can be further divided into a point anomaly, which is an outlier compared to the complete time series, and a contextual one as an outlier with respect to a subset of data within a time series. By contrast, we have the sequence-based anomaly, which is defined as a sequence of data that do not follow a typical pattern from the past. In the literature, we have the noise anomaly, where the amount of noise is much bigger than the rest. The speed-up anomaly, where the period gets shorter and shorter. And the scale anomaly that simply scales the amplitude of the period. The flip anomaly that flips parts of the time series. And in this research, we propose other three types of baseline anomalies that are local acceleration LA anomaly, that change the baseline of the time series from a constant local trend to a constant local level, and the local trend anomaly that shifts the local trend from one to another, and the local level anomaly that change the level in one time step. Why we care more about these three types of anomalies than the other is because in the context of structural health monitoring, the other anomalies are usually caused by sensor faults or environment issue. And these three anomalies are typically associated with structural deterioration, which could develop over years or even decades. So what are the criteria of an effective anomaly detection method? Firstly, it has to correctly identify the unusual patterns. We want it to detect anomaly within a time window. When anomaly happen, we don't want to be notified after 10 years. And it has to be reliable within a wide range of anomaly magnitude, not only on those crazily big anomaly that we can already visually see something is happening. But also on those tiny anomaly. Before we can visually see it, the algorithm already detects it at an early age. Last but not least, it should allow a trade-off between the anomaly detectability and the false alarm rates. Imagine the fire alarm in your apartment is super sensitive. Of course, when fire happens, it will notify you, but you may also get false alarm every day when you cook because it's super sensitive to the smoke. That's something that you certainly don't want. And on the other hand, if it's insensitive, you will not get those false alarms every day, but it cannot save you from fire neither. So between these two extremes, the super sensitive and the insensitive, we want to find something in between that is just correctly sensitive enough. And to do this, we need a trade-off between the detectability and the false alarm rates. So how it works. Here, I prepare a demo from the elongation measurements on a bridge in Montreal from 2019 to 21. I imported it in Python. This is the same time series as we saw in the slide. The second plot is the probability of anomaly, which remains at 0 all the time because the original time series is assumed to be anomaly free, given that no events were recorded in this period. And on top of this time series, I will introduce the anomaly that shifts the zero speed to a constant speed. So this time series, it drops after this point where the probability of anomaly goes up to 1. And we can already see it from our eyes. And this period is obviously much lower than the previous two. And this is an abnormal pattern. And so as our model, they can detect this anomaly quite early, like within 1 month. And the models include autoregressive components, that's AR here, and a bounded autoregressive component. If I further reduce the magnitude of this anomaly, and now it gets more difficult for us to say that this is abnormal, and so as our models. So the AR models will take more time to detect this amount of magnitude. The BAR, you can still identify it like within maximum 3 months. And if I further reduce it, even the AR model would miss this anomaly, and our BAR can still identify them. To understand the BAR model that's proposed in this paper, we will firstly go through the mathematical preliminaries, and we will see what is the autoregressive components that is currently used in our model. We will see in section 3 how we can improve these AR components by putting boundaries on it. And we will quickly go through the evaluation metric that we use in the experiments based on a synthetic time series and a few real time series measured on a dam in Canada. I will wrap up today's talk by giving the conclusions. So the key findings of our research includes an evaluation metric that considers all the detection criteria that we just saw in the last slide, and a new component that allows early detection of anomalies and has the capacity to detect smaller anomaly magnitude and allow the trade-off between the anomaly detectability and false alarm rates. All the work in this study are built upon Bayesian Dynamic Linear Models, that's BDLM here. It has 2 steps. The first step is prediction. In the prediction, we firstly have the transition model that transfer our knowledge of the hidden state x at time t-1 to time t by using a transition matrix and a process error that is modeled by a Gaussian distribution with 0 mean and Q variance. The output of the transition model is the hidden state estimates at time t given all the observation from time step 1 to t-1, and we estimate the moments of it represented by the mu and sigma, the mean value and the variance. Subscript here means that these are the estimates at time step t given all the observation up to t-1. And after that, we will pass our hidden state to the observation model by the observation matrix F and the observation error Vt modeled by a 0 mean and R variance Gaussian distribution. And the output of the observation model are the moment estimates of the observation, of the predicted observation at time t given all the observation up to t-1. And we can also compute the covariance between the hidden state and the predicted observation at time t, which will be used in the next step, the update step. In the update step, we will update our predicted estimates of the hidden state by using the true observation. So to update the mean value of the hidden state, we compare the difference between the true observation and our predicted expected value of the observation, and multiply by this covariance term and variance term and update the expected value. And we can do the same to the variance estimates. And this is the flowchart of BDLM, where we begin from the hidden state at time t-1, and the dot here means the hidden the components used in BDLM. We pass it through the transition model, we get the estimates at time t, and we pass the hidden state estimates through the observation model to get the predicted observation and compare it with the true observation so as to do the update step on the hidden state. And then we can pass our hidden state estimates to the next time step and do it in iteration until we finish a time series. Here I am providing the minimal explanation of BDLM for those who are new in this field and want to know more detail. I would recommend to read the section 12 in the machine learning book written by Professor Goulet, or check out the lecture video of state space model in this channel. So what are the autoregressive components? In BDLM, we use different components to model different parts of the time series. For example, we have baseline components, we have periodic components that model the periodic patterns of the time series, and here autoregressive components is used to model the residuals. The matrices that defines the AR components are A, F, Q with superscript of AR. The transition matrix A is defined by the autoregressive coefficient that is constrained between 0 and 1. And the F matrix is defined by 1, means that the residual component is observable. Whenever it is 0, that means that component is not observable. And the QAR is defined by the sigma AR. The stationary standard deviation can be computed by using this formula, by using sigma AR and phi AR, and this is one example of the realization of the AR components throughout different time series using phi AR equals to 0.8 and sigma AR equals to 0.5. We can see that by using a phi AR value between 0 and 1, we have the realization of the AR that is quite stationary. So from a generative point of view, by using the phi AR between 0 and 1, it can generate the time series that is stationary. So what's the issue of using AR components in BDLM? The issue is that when the update step using the true observation y is involved, we observe a drift in the residual component in some cases. This is an example. The y is the measurement. It is generated by a local level for the stationary region and a local trend for the non-stationary region. The residual, the true value of the residual is stationary, and the pi means the probability of anomaly. It goes up to 1 at the middle of the time series. So this is what I got from the estimation. So the residual estimation represented by the purple line here, it drifts away from the true value after I injected the anomaly. And these drifts hinder our anomaly detection. So why this would happen is typically caused by a phi AR value that is close to 1, which implies strong dependency exists between residual values. And it happens typically when the baseline or periodic components are not correctly defined. And the patterns of them may be partially attributed to the AR components and eventually lead to a phi AR close to 1 to enable the model to capture the strong dependency between the residual values. And it may also happen when super small time steps are used. For example, if we collect our data every hour, and the prediction as well as the prediction error will be similar between each hours. And to capture this high correlation, the model will use a phi AR close to 1 to capture it. And this will cause the issue of the drifting in the residual. So the solution of it is to constrain the AR estimates within a boundary. But by doing so, we face two challenges. The first one is when we modify the estimation, the residual estimation, it is important to remain the accuracy of the other components estimation as well. And the second challenge is to maintain the analytical traceability of BDLM. That means for each time step, when we truncate the AR hidden state that is modeled by a Gaussian, we need to keep it as Gaussian as well, so as to use all the closed form solution that we saw in the preliminary section. So this is our idea about putting the boundary on the AR components. Given the same time series and the same drift that we saw as in the last slide, our idea is to pass the AR estimates through an activation function phi that is defined by a lower and upper bounded value function. And for all the estimates that are outside the boundaries, they will be collapsed at the boundary values. And for those in between, they will be capped by this linear relation. And the boundary value B is determined by multiplying a gamma value with the stationary standard deviation of AR components. And by doing so, we will have a stationary residual component. This slide is to provide more detail about the activation function that is called Mixture Rectified Linear Activation Units, MVLU here. So the inputs of MVLU are the moments, is the distribution of the AR hidden states at time t. And we pass it through this function. All the estimates outside the boundary, the yellow parts as well as the blue parts at the right hand side, will be collapsed to 2 points at the boundaries. And those in between will be capped as the dashed line in the third figures here. And we can compute the moments of the truncated Gaussian parts and approximate it through a full Gaussian. And in this way, we will have 3 Gaussian components that are represented by blue, yellow, and purple color here. For the blue and yellow parts, they are 2 values. They can be regarded as 2 Gaussian with 0 variance. And their probability is the cumulative density function CDF at the boundary values. And for the Gaussian components that represents the truncated parts in between, we have the probability here, and we have closed form solution to compute its moments. And these equations can be found in our paper. And after that, we can do a Gaussian mixture of these 3 components and get our outputs, which are the moments of the BAR components. And this line summarize the inputs and the outputs. So the inputs are the moments of the AR components as well as its covariance with other components, and a hyperparameter gamma that help us to decide the boundary values. And the outputs of it are the moments of the BAR as well as its covariance with other components. So how to incorporate BAR in the BDLM framework? The hidden state vector is augmented by the XBAR, and the transition matrix remains the phi AR in the position of AR, and for all the position that's related to BAR, they are 0. That means BAR is not involved in the transition model. And for the observation matrix, the BAR is involved, but the AR is not observable. And we also have the Q and R that defines the process error and the observation error. And we expand the flowchart of BDLM to the BDLM BAR framework. So for all the modification, we use the purple color to highlight it. We begin from the hidden state at time t-1. This is the same as BDLM. We pass them through the transition model using this transition matrix A, and the BAR is not involved in the transition model. That's why here is empty. Then before passing to the observation model, we will pass our AR estimates to the m-value function and get the BAR estimates. And then we pass them to the observation model, and we get our predicted observation, compare it to the true observation, update, and go to the next step. So the rest will be the same as BDLM. Until this point, we've seen the mathematical preliminaries of BDLM, and we see what is AR and BAR components. And now we will go through the evaluation metric that we used in the experiment. So why we need a new evaluation metric in this study? A small recap is the trade-off between the anomaly detectability and the false alarm rates. We don't want a method that is super sensitive, that provide false alarm every day, and we don't want it to be insensitive. And in the case of BAR, the sensitivity of a model is controlled by the boundary, and the boundary is computed by the multiplying gamma with the sigma AR0. When gamma equals to 2, it represents a 95% coverage region that is indicated by the pink color here. We have another time series with an anomaly beginning at the middle. By using this constraint, the model can detect the anomaly almost at the end of the time series. And this performance is okay, but can we get a more sensitive model and detect it earlier? The answer is yes. If we use a smaller gamma value, we have a smaller boundary width, and it provides better constraint, and the model can detect the anomaly much earlier. But is this a universal trick that I can always keep decreasing my gamma value and I will keep getting a better model? The answer is no. If a model is too sensitive, that means I am putting too much constraint on it, and I'm using a too small gamma value. The model will provide alarms everywhere, and this is something that we don't want. And what if we go to the other way by putting the gamma value as infinity? And in this case, we are putting no constraint on the AR estimates, and it's the same as the AR model, and it becomes insensitive and cannot detect this anomaly. So we see to look for a better trade-off between detectability and the false alarm rate, we need to select a correct gamma value. And to select a gamma value, we need a metric to quantify how good it is. So in this paper, we use a score that is called F1T to evaluate it. F1T is computed based on the existing F1 score that is defined by TP true positive, FP false positive, and false negative. So they are defined by this table. When the true case is anomaly is present and a model trigger an alarm, then it's a true positive. If there's no anomaly in reality and the model trigger an alarm, then it's a false positive. that's false alarm. And when anomaly is present and the model triggers nothing, then it's a false negative. In terms of time series, we will count this metric in time series wise. For each time series, we will introduce only one anomaly. If the model detects the trigger and alarm before we introduce the anomaly, then it's a FP and it will be augmented by 1. And if it triggers an alarm within the region that we introduce the anomaly, then TP will be added by 1. Whenever it doesn't trigger anything, it missed the alarm, or it trigger an alarm after the detection window that we defined, then a false negative will be augmented by 1. But until now, there's still something missing here. The issue is in the determination of TP. When we count the TP, no matter where the model triggers an alarm within this region, it always gets a TP augmented by 1. So if you trigger right away after we introduce an anomaly, or you trigger at the end of this anomaly region, it has the same effect to our evaluation score. So it neglects the detection time here. To consider the effect of the detection time, we propose the F1 temporal score that simply multiply the original F1 score by a lambda value. And the lambda value, it remains at 1 when the detection time is smaller or equals to 0, and gradually decrease to 0 when the detection time reached the length of the detection window. Whenever the detection time is smaller than 0, that means it's a false positive because it detects it before we introduce an anomaly. But here, to avoid a double penalty, we keep it as 1 because the FP is already penalized in the original F1 score. Okay, now we are ready to see the results from the experiments. The first experiment was done based on the synthetic data that we saw, which is generated by using the local level for the stationary regime and local trend for the non-stationary regime overlapped by the residual. These are the results given by AR and BAR components. The horizontal axis are the time, and the vertical axis we have the estimates of AR components of local trend of the observation and the probability of anomalies. So when we use the AR components, we see the drift in the AR estimates, and the estimation of local trend is not accurate after the time series switch to the non-stationary region. We can see that it cannot identify the true value of the new local trend, and it provides more uncertainty in the prediction of observation, and it detects the anomalies like 4 to 5 months later. While if we use BAR, all our residual estimates stays in the stationary region, and it can identify the true local trend with smaller uncertainty in the observation prediction, and it can detect the anomaly much earlier, less than 3 months. And we know that it works on synthetic time series, but how about its performance on real time series, which are way more complex? So I run both models on 8 time series measured on a dam. These are the names of the time series that begins either with A or M. When it begins with A, it means this is the time series that was automatically collected with more observation. And when it begins with M, it's a manually collected time series that has less observation. And they measure either the crack opening or the displacements of the dam, and the span of this time series vary from 7 years to more than 10 years. The data period, the collection frequency varies from half of a day to a month or 3 months. The components we use to model this time series are local trend for the stationary and local acceleration for the non-stationary in terms of the baseline modeling. And for the to model the periodic pattern, we use either a kernel regression with 10 control points or a periodic component. And we have the residual as AR and BAR components. In the following slides, we will focus on this time series, which has only 39 data points. So this time series measures the crack opening of the dam and is represented by the black line here. Horizontal axis are the time and the vertical axis shows the crack opening. And by using this real-time series, I can generate a bunch of synthetic time series that are similar to it. And this time series, for sure, I know they are anomaly free because I didn't change the baseline in the data generation. And on top of this time series, I will inject different types of anomaly that we saw in the context section, LA, LT, and LL anomaly. And I evaluate the performance of the BAR model with different gamma value represented by the horizontal axis here, compare it to the AR components. And the vertical axis here, for the first graph, we have the anomaly magnitude, and the third dimension of this graph is represented by the color here, which shows the detection time. And for the second row, we have the same vertical axis, but this time the color shows different detection probability. And the third row shows the number of false alarm per 10 years. And the last row is the F1T score that aggregates all the above aspects. And it considers not only the detectability but also the false alarm rates. So here we just take one example. Let's see the time series with local acceleration anomaly. Given this anomaly with a gamma value, with a small gamma value, the model is super sensitive and it will produce false alarm rates that is crazily high, more than 10 false alarm per 10 year, which is not acceptable in the context of SHM. But at the same time, it can detect the anomaly, super small anomaly with short detection time and high probability. As we increase the gamma value, the false alarm rate is reduced pretty fast, and within this range, it still remains a good detectability with short detection time and higher detection probability compared to the AR components. But if we further increase the value of the gamma, and it will gradually converge to the AR components. So now that we verify both models' performance by using the synthetic time series similar to the real one, and the next step is to validate our results by running them back on the real time series. So this shows the result from the validation part. The horizontal axis here is the anomaly magnitude, and the vertical axis for the first plot shows the detection probability. The second plot is the detection time. So here the gamma value is fixed to 0.4 because we want a false alarm rate to be lower than 1 false alarm per 10 year, which correspond to the gamma value of 0.4 here. So with BAR 0.4, the anomaly the smallest anomaly that you can detect is 2e minus 5, and the AR is for the AR is 7e minus 5, and the BAR constantly shows a higher detection probability than the AR component with shorter detection time, that almost twice faster than AR. And these results match our results in the verification, because take this line as an example. When the anomaly magnitude equals to 2e minus 5 millimeters per year square, and the detection probability for the BAR would be close to 100%, while for AR would be only 60%, and the AR needs a detection time between 3 to 4 years, while the BAR needs a time that less than 2 years. So if we go back to see our verification results, so given an LA anomaly and gamma equals to 0.4 here, for the anomaly of for the anomaly magnitude of 2e minus 4, it will stay at this range, so it's close to the blue color. When it's close to blue color, is close to 1 to 2 years. It needs 1 to 2 years for the detection, while the AR is more in the yellow region, that's around 4 years, and that matches what we just saw in the validation results. And in terms of the probability, the BAR with gamma equals to 0.4 has a detection probability that is 100%, and the AR has a probability of 60%. So the result from the verification match our validation results. That means it is a good representation of the both models' performance on real time series. And these two aspects can be aggregated to the F1T score, which are listed here with LA anomaly, and the horizontal axis here is the time series on the time series of M08C and local acceleration anomaly. This model have the F1T score as here, and we repeat the same process on other 7 time series overlap with different anomalies, and the BAR with the optimal gamma value here constantly shows a much higher F1T score than AR components, especially in the time series with LA and LT anomalies, where the time series where the effects from the anomalies are accumulated through times. To wrap up today's talk, the BAR model surpasses the AR model with an improved accuracy at estimating hidden states. It allows an early detection of anomalies, and it has the capacity to detect smaller anomaly magnitudes. And last but not least, it has the ability to control the trade-off between the anomaly detectability and the false alarm rates.